In this room, we will have workshops, one about green hydrogen, followed by another workshop about methane. Now we will start our plenary session program. We would like to invite Dr. Amr Al-Hinai, Deputy Vice Chancellor for Postgraduate Studies and Research at Al-Qaboos University, the chair of this plenary session, to the stage to start the program. Thank you very much.
بسم الله الرحمن الرحيم. السلام عليكم جميعا. Very good morning, ladies and gentlemen, and would like really to welcome you all to this plenary session. It's my pleasure to chair the session today, and we are really lucky to have all of our keynote speakers to participate in this session today. We'll try to adhere with the time. I know that we are a little bit late, but also at the same time, in fact, two of the speakers, they apologize, they will not be joining us today. So the presentation will be limited to about 10 minutes. And after that, we'll move to the next speaker. And at the end, we'll have time for questions. So please take note of your questions, and then we'll have Q&A at the end of the last presentation. So the speakers will come to the stage. They will introduce themselves. I know most of you probably had the chance already to meet them, but it's good to have a brief introduction about yourself. We'll start with Prof. Sergio. So yeah, welcome to the stage and start your presentation.
Good morning, everybody. My name is Sergio Mosmani, like you can see in the first slide. I'm a chemist, industrial chemist by profession, but I've been involved in environmental issues and environmental consulting for the past 25 years. So I would like to thank the organizers for the invitation, and let's start. My presentation is called When the Path to Climate Change Mitigation Needs Reengineering, Think Out of the Box. The next slide, please. Oh, sorry. There will be about 4 different moments in this presentation. First, about the different economies that are important in order to make the change. I will talk a little bit about the methane emissions and opportunities, since this conference deals mostly with this topic. Later on, I will speak about the planetary boundaries and the third horizon. And finally, the energy for change, if we want to change. The economies around, basically, you will heard about the circular economy, the knowledge economy. Perhaps you have heard about the feeling economy, and finally, the donut economy. All of them have something to contribute in order to make the changes that we are looking forward to have. The donut economy is a very interesting one, and it suggests that we should design our future and design with the regenerative way of thinking. The feeling economy will deal with the impact of artificial intelligence in all the sectors of the economy, and how we need to have empathy for our people and really care for the people. The circular economy is well known, has been around for a little while, And what I want to highlight is that around this economy, cost savings and some advantages could be observed. Finally, the knowledge economy that has been around much more longer. I will just highlight that we need to take serious consideration for the environment. We have only one planet. We know a lot about the planet. We know a lot about the problems. We know about the solutions, but we need to move in the implementation phase. And how the knowledge might change the path, and what pieces are missing, and how to find those pieces of information or knowledge that are missing. That takes me to this development model that is called the regenerative development model, and contains some of the issues that apparently we have lost along the years. The spirituality, the culture, more earth as one of the principles, the economy, society, and politics. All of them in this figure will contribute to a different way of seeing the development in the future. The methane emissions from the industry, just a quick overview. This is from satellite measurements from the Tropomi system, and they show more than 1,800 single releases of methane around the world, and they are counting only the ones above 25 tons per hour, and that's a high threshold value for measuring. It is interesting to understand that about 22% of those emissions, methane emissions, could be solved with good practices. And they will be non-regret measures, about between $100 and $400 per ton of gas that is losing the sector because of these releases. So here we have one of the pictures coming out of this program. And you can see here the plumes from 12 different sources. And they account for 50 tons of methane coming per hour. That's a lot of methane being released. The other system that I want to highlight is the EMIT system from NASA. And you could see also here the measurements, some of those 50 tons per hour also in the US, some that will account for 18 tons per hour. That's again huge amounts of methane being released to the atmosphere. So what should we do? It's a matter of keeping in good shape the operations. Good housekeeping is very important for this effort. And you can see in the green bracket to the right that you can reduce about 20% of those emissions in the next 20 years. And that will be interesting for the environment and interesting for industry. Now, regarding the planetary limitations or boundaries, this is in the middle, the planet, and the surrounding area in green and gray is what the capacity of the Earth to sustain life might have. And beyond that limit, in orange, you will find what we are doing right now. So a lot of issues are out of control and will be limiting our capacity for living in the next 20 years. That's why we should start thinking in a different way, change the paradigm, and instead of the red line, which is the Horizon 1, business as usual, doing business as every day we're doing, change that for the Horizon 2 as a transition period where you will start doing innovation, and then hopefully think more about the future and come back from that future to the present and see what needs to be done in order to reach that state. And that's the emerging future that we should develop in the next years, hopefully yesterday. And that comes with a lot of innovation and thinking out of the box. What could we do different? And at the end, I want to just talk about change. And this takes me to the energy for change. The entry point will be the desirable part, that is the human part. Humans are the ones taking decisions. Humans are the ones making strategies. Humans are the ones who, at the end, could make things better or worse. Then the physical part that concerns the technical issues, I believe that's the easy part. And I have told my previous boss in UNIDO, you don't need a PhD in sciences to talk about these issues. What you need is a psychologist or a persuasion specialist, a social person, social scientist who can dig into your minds and make you change. And finally, the economics that should be viable. And in the middle of everything is the innovation portion. We should do a lot of research, development, and innovation in order to reach this level. And that is attached to this equation. C is the energy for change and has three contributions. Contribution A is the dissatisfaction with the status quo. Are we satisfied with what we have? Are we happy with what we have? Or we really think that we need to change? Then A will be, you will put some value for that dissatisfaction level. B is this desirable condition. Are we clear on what we need for the future? Do we have clarity on where we want to be in the next 20 years? Or we are still thinking, well, I'll wait 5 years, I wait 10 years to take the decisions. And D is a very important part. The first practical steps. Don't try to run at the first time. Let's walk, let's take the first step, and eventually, when you get the conviction and you know that it's feasible, then you will start getting the idea of let's move forward. At the end, in this equation, the cost of change, that is X, is the material and emotional cost. It's not just the cost of financing certain changes. It's the emotional part also. Do we need to change and we agree to change and we feel that we need to change? That's the emotional part. It's not the economics. And finally, the changes with new models and business models. There are a lot of discussions in the chemical sector about what's the future. And most of the discussions go around CO2 capture, like you have in your proposal for 2040. And besides that, strong electrification also. And besides that, using hydrogen for certain processes like making syngas, and from there start making alternative fuels. That will have a double effect. First, capture CO2, lowering the amount of CO2 in the atmosphere, and secondly, eliminate the CO2 coming from fossil fuels. And like it is at the end, easy? Maybe not. Nothing is easy. But it's a matter of having the decision, the will to make it. And the last slide is this message from Buckminster Fuller. You never change anything by fighting the existing reality. To change something, build a new model that makes the existing model obsolete. So we don't need to fight. We don't need to go against one and another. We need to join hands and figure out what the new model is. Thank you very much.
Thank you, Prof. Sergio. We'll move to the next speaker. The coming next speaker will be talking mainly about methane. Our first speaker is Dr. Ank from Germany. So please.
Thank you. Oh, this is not my talk. So my name is Anke Reuger. I'm from DLR, German Aerospace Center in Oberpfaffenhofen in Germany. I'm a physical chemist, so experimental scientist, and we are doing measurements of methane and also other trace and greenhouse gases. First of all, thanks for the invitation to this very important conference, and I have to say that I really enjoyed the day yesterday, and I was impressed by the high quality of the talks I listened to. And today in my talk, I will talk about methane emissions and studying methane emissions by doing measurement studies. My talk will be a little bit more general, showing the methodology, and the next talk will then focus on a study we are planning in Oman, and then this is followed by a talk showing results from an earlier measurement study. So next slide, please. I have to do it myself. Okay, so I will keep the introduction very short because everybody here is aware of climate change and everybody knows that the main driver is anthropogenic greenhouse gas emissions. The three most important anthropogenic greenhouse gas emissions are shown here. You can see the time series of atmospheric measurements of these greenhouse gases. We know that carbon dioxide is the main driver. However, there are also two other very important greenhouse gases, which is methane, which is what we are talking about today. But I will shortly mention also nitrous oxide, which is the third most important anthropogenic greenhouse gas and is released mainly by agricultural emissions. So here we want to focus on methane. Methane has a variety of different sources to the atmosphere, both natural and anthropogenic. So natural emissions include emissions from wetlands in the Arctic and in the tropics. But here we are talking about reducing anthropogenic emissions because, of course, the only way we can do something is to reduce anthropogenic emissions. We can't do anything about the natural emissions. The main sectors where methane is released include agriculture, waste, so from landfills, and fossil fuel exploration. So methane matters. Why? we know that methane, on a molecular basis, is much more efficient in trapping infrared radiation than CO2, and this is expressed in the global warming potential, which is given on different time frames. So in a time frame of 20 years, methane is roughly 28 times more efficient than a CO2 molecule. And currently, methane already contributes a lot to anthropogenic radiative forcing, roughly a quarter. There's one good news, let's say, about methane, which is the lifetime. The lifetime is only 10 years, so minimum a magnitude lower than for CO2. And the basic message is that if we can reduce methane emissions now, we will have a positive effect at short timescales, exactly what we need. So we know that more than half, so roughly 60% of methane emissions is anthropogenic. And on the right-hand side, you can see again observations of methane. So these are not emissions reported. These are real observations. This is the methane concentration measured on a global average. And you can see that methane increased during the last 40, 50 years. But what you can also see, so is there a pointer? No. What you can also see is at the end, where it's written methane surge, the concentration increases faster and faster, and we had the largest increase of methane during 2020 and 21. So this is really threatening, right? So methane concentrations are increasing faster than ever. That's the basic message. So, I'm sorry. What we want to understand is what, in this increase of methane concentrations, what is the impact of the different anthropogenic sectors? What is the role of oil, gas, coal, so fossil fuel, basically, from landfills and from agricultural sectors? So we're doing studies in all of these fields, and we want to better understand how much is emitted, when, where, what are the processes behind, are there even unknown sources? And all these information is needed to develop efficient mitigation strategies. We have to better understand the sources to really develop efficient mitigation strategies. So where are we right now? Again, you can see here a time series. The red or the colored lines give you the IPCC scenarios. So IPCC develops different kind of scenarios for the futures. And these are, again, concentrations. And what you can see is the blue line. This is the Paris trajectory. Yeah? So decreasing concentrations, basically. The red line is the worst scenario IPCC could think of. And if you look at the black line, you can see the observations, and you can clearly see, and again, this is threatening, that we approach the worst case scenario, especially since methane is increasing faster and faster. So this was all realized by the politicians, and they launched the Global Methane Pledge. I'm quite sure that you know about this. This was announced in Glasgow at the COP26. And it was announced by the EU and by the European Commissions and the US. But for now, over 100 countries have joined, and also Oman joined the pledge, which is a very good news. And the countries who committed to join the pledge, they commit to reduce the global the methane emissions from their countries, so globally, across all methane-emitting sectors. Although we have to say that we are starting with the fossil fuel sector because these are kind of the low-hanging fruits. They also commit to improve the national greenhouse gas reporting, meaning they want to increase the transparency, and also to support international initiatives like the IMEO studies within UNEP. So we heard about this in a talk yesterday, and all the studies you will see in the next 2 talks are also financed by the IMEO program. Again, the Global Methane Pledge is the key initiative, which is followed by this IMEO program. You could think that IMEO is kind of a monitoring, verification, reporting activity somehow. I think it's a little bit more because it really wants to better understand the emissions, to provide actionable data. And IMEO so aims to better understand and quantify the anthropogenic methane emissions through different kind of measurement studies, like the studies we are planning here in Oman. So the question is, how can we better understand, quantify, verify, and reconcile these methane emissions? What is usually done to calculate emissions is the so-called bottom-up approach. This is based on statistical data. The most basic approach just assumes that, for example, for the agricultural sector, you take the amount of methane which is released by a cow, multiply this by the number of cows, and you can do this for all sectors, for all gases, for all regions, and then you can get a nice emission map. This is a very good start, of course, to get a first picture, a global picture. However, we know that we don't have exact data. So a cow does not emit the same amount of methane everywhere. Yeah? So data are limited, data are not correct. And this is why scientists started, I think even 20 years ago, the so-called top-down approach, which uses observations. It goes the other way around. So we take measurements from satellites, from aircrafts, from the ground, and then calculate back to the emissions. Yeah. And this is a very independent approach because we are not relying on data. We are using real measurements, real observational evidence. And you can do this top-down approach on different scales. Here in Oman, we will do this on a regional scale or local scale using a helicopter. There's one or two disadvantages. Of course, it's challenging from their methodology, but there was a lot of effort put into these top-down observations and improving these top-down observations. So we learned a lot during the last 10, 15 years. The other thing is that, of course, it's limited by resources. You can't do measurements all the time, everywhere. But to sum up, these top-down observations, so we can learn from an intercomparison between bottom-up and top-down. With the top-down observations, we can independently measure the emissions, verify the bottom-up emissions, and if there's a large difference between bottom-up and top-down, these measurements can help to identify the deficiencies of the bottom-up estimates. And of course, from these deficiencies and all the measurements, we can learn for mitigation planning, and we can really drive on-the-ground solutions. So what do we need for a successful top-down study? First of all, you need a measurement system, and you need a measurement platform. Different kind of methods are used for these top-down studies. I don't want to get too much into the details, but just that you heard of that, it's first of all in situ measurements. This is what we are doing here in Oman. You can see a map where we scanned the plume. It's point measurements along the path of the helicopter, of the aircraft, and you can really scan the plume, and the measurements are highly sensitive. That's the main advantage, and you have a very high spatial resolution. The other approach, which we already saw some pictures in the previous talks, is passive remote sensing. Here you get column observations, and the nice thing about this method is that it has a possibility to really take pictures, let's say, so to image the plume. But the accuracy is limited, and especially here in Oman, where you might have sea salt or dust, it's really difficult to use these satellite information. And then there's also active remote sensing. This is more going into the future, where you don't rely on you don't need the sun as a light source, but you take your own light source, which is a laser, and this means that you have much higher accuracy. And all these methods can be deployed on different kind of platforms, satellites. I think this is the main tool in the future. There was a lot of development during the last years. Basically, you decide between the survey missions, the global survey missions, like TROPOMI, for example, but there's also the target approach, where you really look at specific targets with a high spatial resolution. So the GHT satellite is one example for this, but there are more to come in the next years. And then you can deploy these instruments also on other movable platforms like aircraft, helicopters, drones, or cars. And you will hear about these methods in the next talk. So now, if you have the measurement system and the platform, you have to have an appropriate measurement strategy, which really can depend on where you want to measure and let's say, the emission landscape looks like. Here's one very common approach shown, which is the mass balance, but I have to say that there are also many other approaches you can use, but this is a very basic one. Okay. So here you can see the USCB, that's in Poland. You can see the ventilation shafts, so methane is emitted by when the coal is cracked, and the methane is released directly to the atmosphere. The wind in this case is coming from the left, and we just draw a box around it, yeah, and want to quantify what's going into the box and what's going out of the box. And basically, this is how we measure this with the aircraft. So we try with the upwind leg to calculate what's coming into the box, and then with the downwind wall, what's going out of the box. And then by simply taking the difference, we can really calculate what's emitted inside the box. So we, at DLR, we did a lot of studies during recent years just to show that we not only look at methane and not only look in the oil and gas sectors. So we did measurements of coal mine emissions in Poland. We looked at urban emissions from the capital in Germany, Berlin, and we also looked at agricultural emissions, in this case not methane but N2O. And sometimes we found a good agreement between bottom up and top down, and sometimes there was a larger discrepancy. So this is my last point. If we want to do international studies, we need local partners, we need local experts. So a very good collaboration with local partners is really essential for conducting these measurements. So we need contact to authorities, to the industry, to scientists. And I just want to show one example from a recent study in Africa, which we did within the IMEO program. With our own aircraft, which is the Falcon, we've been based in Libreville. So this is, you can't see it here, but it's Africa, the Central Africa, the western coast, and we did measurements of the relevant oil and gas clusters offshore of Gabon and Angola during a 3-week mission last September. And this mission was only possible because we had really excellent collaboration with local partners from Ageos. So you can see here pictures from the team, the local team and the DLR team. We had visit from partners in Angola who learned how to measure methane, how to operate the instruments, and we also had a public day where the ministries and industry could come to the aircraft and have a look at the measurement systems. And the collaboration is ongoing to discuss and exchange the data transfer and to assure that there's really a transfer of knowledge as well. So the take-home message is basically methane matters. We have to do something. We can use top-down studies to learn something about understanding methane emissions. And we need a close collaboration between industry and scientists. And maybe just the last point, it's a lot of work preparing these studies for us and also for the local partners, but I think the effort will pay off because there's a knowledge transfer to both sides, and we also want to build up a capacity in the countries where we're doing the measurements. So thank you. I'm sorry.
Thank you, Dr. Rank. And then we'll move to our next speaker, Dr. Heidi, again from the Aerospace Center in Germany. And probably the focus this time will be in the oil and gas in Oman. Please.
So first of all, I would like to thank Professor Yassin Sharabi for organizing this very nice conference. So thank you so much, and also for inviting me for here. So yeah, this talk is about methane emissions from industrial activities, and I will present a novel technique that we used in Poland, and also how we could apply this method to Oman. Okay. So these are some news that you could read in the Muscat Daily and in the Observer about the global methane pledge. So Oman committed to join the global methane pledge, which is a very nice news. And so it's about reducing the methane emission until 2030 about 30% globally, and Oman decided that they will try to reduce the emissions by 7%, as stated here. And I will try to explain one possibility how we can do this. So in the last talk, you also heard about IMEO, the International Methane Emission Observatory. And one of the key messages in the last report was that more accurate data will enable more targeted action. So we need urgently improved methane emission data to reduce global warming, and this needs also, IMEO wants to integrate data from company reporting, satellite, and also scientific studies. And this is where we come in. The German Aerospace Center, also called the DLR, is the equivalent to NASA in the United States. So who are we? We are located in the southern part of Germany, close to Munich, in Oberpfaffenhofen. We have about 10 institutes located there, and we also have an airport, as you can see here. And we have a large air fleet consisting of at least 10 different aircraft of different sizes, as you can see here. And we have been all around the world with these aircraft, except the Arabian Peninsula up to now. So in general, it's difficult for us to receive all the approvals for the Middle East to make measurements, and this is why it didn't happen up to now. So our team is specialized in airborne in situ measurements of short and long-lived atmospheric trace gases as methane, for example, CH4. And this picture you saw before in the first talk, it's showing satellite data from satellites indicating where you see the methane hotspots around the globe. And first we will concentrate on the methane hotspot in Europe, which is located in Poland. And this comes from coal mining activities. And I will also introduce the most recent measurements that we carried out in the last 2 years, where we focused on methane and SO2 emissions. So we just the first one was methane to go Europe and methane to go Africa. You just heard about from Anke, from my colleague, where we used the Falcon, DLR Falcon aircraft to probe offshore gas and power plants and also offshore oil activities. And the most latest experiment was carried out in Poland, where we probed the coal mine ventilation shafts and where we, for the first time, also used a helicopter for the measurements. And the advantage is that it's easier for the flight permission handling if we use a local helicopter company. And we were able to do flights at very low altitude and also close to the facilities compared to our big aircraft. And what we plan for this year in autumn is to go to Oman and to probe the onshore oil and gas facilities. And this is the setup of the campaign that we did in Poland. So we have a helicopter towed probe hanging below the helicopter, and this probe is called helipod. And it was equipped with a number of instruments, as you can see here. So we carried out measurements of methane, of CO2, and aerosols. And important is also the meteorological sensor, where we also have 3D wind measurements on board. And you can see here on the top of the picture some ventilation shafts from the coal mines. And also in the center, the small picture, we have a helipod mission monitor. This means that we can follow the measurements inside the helicopter online, which is very useful to direct the helicopter in the perfect direction to probe the emissions. And this is from a publication of Conley, from some colleagues in the US, how they did this with a small aircraft. So you can see very nicely the plume coming out from the facility. So in this case, methane is invisible. We don't see it like in this picture. This is just to show how it works. And what the idea behind this is that you have to capture the whole vertical extension of this plume. And this is why you fly several circles at different altitudes, and at the end you get a kind of curtain, as you can see on the right. And we need this kind of curtain measurements combined with wind measurements to estimate the methane mass flux coming out of the facilities. And this is how our flight patterns looks like with the helicopter. So with the helicopter, it's not possible to turn perfect circles with the system that we used. So instead, we flew a kind of boxes up and downwind of the sources in different distances. So we never fly directly over the sources, just down or upwind, in approximately in distance between 500 meters and up to 5 kilometers away from the source. And here you can also see how the plume disperses if you go further downwind of the plume with time. And here is one of the results from our measurements in Poland. And you can see the orange and the pink dot indicates the facility that was probed. And downwind of this facility, you can see enhancement in methane. This is the horizontal view, and I will show in the next other views where you can see it a little bit better how it works. So this is the 3D curtains, the cross view, also again downwind of the source, the pink point, the pink dot. And here you can see the different curtains that we put inside these measurements, and the idea behind it is to calculate the mass flux of methane for every of these 3 curtains, as you can see. And if you divide it into the 3 different sections, it looks like this. You see here the methane concentration in ppm with altitude for these 3 different curtains. And you can see very close to the source, the plume is low and highly concentrated, and if you go further away, it gets dispersed in the horizontal and in the vertical, and also the mixing ratio decreases. except here is also another source coming in. This is why there is some red enhancement also in the third curtain at the bottom. So we now take these measurements that we have on different altitudes at different distances from the source and multiply them with the wind speed and wind direction to receive the mass flux from methane. And this is what we can also compare with numbers given by the industry. And in Poland, we came up with source strengths of single facilities between 300 and 3,000 kilograms methane per coal mine ventilation shafts. And this is also additional measurements that took place at the ground with the car driving around in the same area. So this will be explained in more detail in the next talk by my colleague from Poland. So again, you can see that we try to put the car at the same kind of racetracks that we use with the helicopter, so that we will receive ground-based measurements at exactly the same place where we were flying. And the results from the ground-based measurements you can see at the bottom. Again, you can see if you move away from the ventilation shaft, indicated with the pink dot again, you can see that the emissions spread and in the horizontal direction. And this is a case where you can see the same shaft probed by different wind directions, and you can see that the plume from methane is going in the direction where the downwind of the wind direction, as you can see. Yep. So let's move from Poland to Oman. And here you can see that what we also did in Poland, that we started to compare our measurements with GHG set measurements. And this is also foreseen for Oman when we come here. And this is some trends of methane published by Professor Sharabi, and where you can also see increasing methane emissions in Oman, and that it's very important that we carry out measurements. And this is also from the Global Methane Assessment, showing that especially in the Middle East and Africa, the methane emissions are expected to increase strongly until 2030. And so far, the different emission inventories in Oman indicate a difference of a factor of 10. And this is why we also need the measurements to improve these uncertainties. And in Oman, as you can see on the right side, there are some hotspots in methane. And if we look more closely to the left picture, we can see that especially, surprisingly actually, this is a very new publication that has been submitted very recently. You can see that in Oman, especially from the oil facilities or exploration, most methane is coming out, not from gas. So this is the result for Oman. And here again, you can see that the methane intensity in Oman is quite high. And we have the indication that it's coming more from the oil than from the gas. So we should try to reduce this methane intensity in Oman. It's important. And this is again the setup that I just explained you. So I will skip this. And where do we want to go in Oman? So we have a collaboration with PDO, Petroleum Development in Oman. And we would like to go to 3 different regions in Oman. So it's the Marmul, the Baya, and the Kwan Alam area. And there is also a memorandum of understanding that we have with PDO and DLR. And here again, the setup, similar as I showed you before, we are going to measure CO2 and methane. And here you also see how the helipod is flying below the helicopter. And here again an example of the flight pattern that we suggest that we do. This is an example for a gathering station. And to do different curtains again, and from these measurements we can estimate the methane mass flux calculation. And in addition, we also plan the ground-based measurements again on roads. So in future, global monitoring of atmospheric methane will be done by a lot of satellites that are coming up. And for methane2go, we would like to compare our measurements with Sentinel-5P measurements, GHG set, and perhaps also the methane set. And so the outcome for you when we would come here would be that you will have a quantification of methane source strengths from individual facilities and clusters of PDO. And you need this data to try to reduce the emission. And as stated in the Global Methane Pledge, Oman envisaged to make a reduction of 7%. And this is my last slide. So my message, my take-home message is, let us hope that we, with our joint activities and efforts, can help to reduce methane emissions. So thank you so much.
Thank you very much. We'll move to our next speaker, Dr. Garslow. Again, talking about the methane, but this time probably an example from Romania. 10 minutes.
Hello, good morning. My name is Jaroslav Neki. I come from AGH University, so this is a university devoted to exploration of oil, gas, and coal excavations. And it is based in very nice medieval or even more older city of Krakow in Poland. This is southern Poland, next to the Silesia region where this coal is excavated in Poland, and in Europe this is the biggest anthropogenic source of methane, unfortunately. And the city of Krakow is called also the city of dragons, and we have a lot of them in Krakow. And one of them was known as a tourist attraction with the flaring methane fire from its mouth. And nowadays it is no more operating due to the political and crisis, and the gas price increases, and the Krakow city decided to switch it off, and there is no more fire dragons in Krakow. So I wanted to show you a bit different perspective. So this will be not the continental or country, or even not the basin, but the single cluster gas well, or even the gas valves measurements, which we could do with the ground-based measurements. So now we are really going down from the tropomi or the satellites, and we step on the ground. So this is the measurements which each operator can do by themselves. So first of all, we need really to say what we are wanting, what do we want to measure, what is our target. And this is, there are many different variables which can be described, and what we are interested in is methane release rate, or just methane release per annual or per yearly amounts. And we will focus now on a point source, which the infrastructure or oil and gas can be the single point source. And we will try to estimate the leak rate. So there are different indirect methods to do it, and my talk will be about indirect, so I will not talk about high flow samplers or any direct approach to your infrastructure or to oil and gas infrastructure or to coal. But the indirect, it means that we will use some kind of the modeling between the measurements and the infrastructure. So we have 3 different, very important approaches. One is mass balance, which was explained already. So we are just taking a cross-section of whole methane plume, which comes out from the source. The second approach is the dispersion model, the very simple model, averaging behavior of the plumes in the atmosphere. They are basing on a dispersion and the let's say the atmospheric processes, diffusion, and basic usually on the eddy diffusivity, so the turbulent flows of the air. And the last one will be more enhanced Lagrangian models, which are also can be used in this Lagrangian model. We are following the single particle released, let's say, by the source. We are just modeling, let's say, 10,000 of the single particles, and we see what is the distribution at the end of the plume. Especially, we can then say how much of the whole plume can be seen by the single receptor pointed at a particular place near the source. So we went mobile. This time we really focused on a car measurement you heard about, but we also supported the heliport campaigns and before the airplane campaigns. We are just driving on the roads and sometimes not on the road, but wherever it's possible. With the car, and all the equipment is installed inside of the car, or it can be taken out. So they are ground-based measurements. So sometimes they are literally ground-based. I mean, we put them on the ground and then we start measurements. And when they are indirect, I mean, we do not touch the infrastructure. You know? We don't approach directly to it. We usually stay in the distance between 20 or 200 or even sometimes few kilometers from the particular source. So here is the gas well in Romania. So one of the methods which we apply, which is the most reliable one and most precise one, requires another gas. And this is called tracer release method. And here you see the cylinder of acetylene, which we place on the balance, and this also the flow is measured by the mass flow controller. And then if it stays next to the real source of methane or any other gases which we want to measure, then you go back and you observe both gases in atmosphere. So you observe the acetylene, which is the red line, and the methane, which is a black line, all together. So it can be done in a way that you just park your car on down the plume, down within the source, and when you measure both gases with the instrument, I will say later which instrument is good for it, and when you calculate the ratio between the methane and your tracer, this is acetylene in this case, and then you can, knowing the release rate of acetylene, you can also calculate the release rate of methane. And this is very simple, very basic, do not need much equipment, do not need very expensive one. Only that you release really the tracer. It can be also N2O, it can be other gases as well. And alternatively, you can drive. So you are releasing your tracer, but you are driving through the plumes forth and back, and then you observe more smooth peaks usually together of the acetylene and methane, and then you calculate the area under this curve, and with the ratio of the areas, you also can calculate, and knowing the release rate of acetylene, you can calculate the methane release rate. And it's also quite convenient if you can drive on the roads next to the infrastructure. It's even more convenient than stationary one. So when you can drive, so here is the example when there was completely no road at all, and we just drive next to the infrastructure on the grass together with the other animals, which also emit methane. Then you can use the Gaussian model. So this is dispersion, simple dispersion model. You treat it a bit inverted. So you measure the concentration and you quantify the release rate instead of what it is normal. The Gaussian models are used. So usually they are used knowing the strengths of the source, they are calculating concentration distribution. But here it's the other way around. So when you drive a single pass through area, this is very shaky and very spiky. So that is very far from the Gaussian peaks, Gaussian distribution curves. So you really need to average. So you pass 20 or 30 times through the plume. Of course, it takes a bit of time. But then you average your measurements, and then you can compare your measurements with the model depending on the situation, how high the source is, and then you can really calculate the strength of this, or the release rate in our case of methane. It doesn't require to go up, but it is really worth to note that this method gives you uncertainty from 20 to 40%. So this is not very precise methodology because you might really lose a lot of methane which passes over the car. So this is advantage to have the helicopter, which flies also at a high altitude, and then using the other techniques. So then there is a method which is maybe not very well known and not so popular, which is called other test method 33A by the EPA methodology. So this requires the anemometer, so ultrasonic anemometer, and a high frequency analyzer of methane, and basis on a very simple equation. You just put your stuff on the ground, put the anemometer on a height about 2 meters high, and then you start to observe the wind with the high frequency, about 10 to 20 hertz, and also the methane concentration with the same frequency. And then you have a forest of the peaks, like here on the picture, and what you need to do is you need to aggregate these peaks to the wind direction, and then average it, and you get some, these blue dots hardly can seen be here. When you fit the Gaussian distribution to them, this is a red dots, and when you calculate the amplitude of this Gaussian distribution, which you use in the equation. So finally, the whole procedure is quite simple. It doesn't require to approach. It can be really done from 200 to even 1 kilometer from the infrastructure, and you need only to park, and all the measurements are done stationary. Okay, yeah, so I will then skip a bit measurement techniques. So there is a variety of the measurement sensors which you can apply. There are catalytic, semiconductor, optical, of course the gas. There is open path dials, so the laser. There are also the closed path laser analyzers, and what we use in our measurement is usually, so this is cavity enhanced absorption spectroscopy systems. There are 3 of them. There is a, I will just go very quickly through them. There is cavity ring down spectroscopy, which is basically produced by the company named Picaro. And they are really nice because they are measuring not only one gas like methane, but also the other. It might be like acetylene, so you have both gases measured by the same instrument at one time. It can also measure the isotopic composition. So if you drive and you find the methane plume and you don't know where it is coming from, is it biological or anthropogenic or thermogenic methane, then it helps you to solve it out. Okay, And this is really the precise measurements. I mean, of course, if you can average your measurements for a longer time, when it even goes super, the precise and uncertainty of measurement is really low. The other one is the so-called optical feedback cavity enhanced absorption spectroscopy produced currently by the LICOR company, and it is more or less exactly the same principle as the Picaro, but the difference comes from the lawyer, so the patented part, and so it is a bit different and it's more handy. We have one here with us here in Oman, and we will try to deploy it in 1 week from now for the test measurements. And it is very precise instrument as for the small suitcase and as for this compact structure of it. And the last one, which we also took here to Oman, is the off-axis integrated cavity output spectroscopy produced currently by the company ABB, and it bases completely on the different, if you will want to know the details, I can explain you separately later. But this is very robust. I mean, you can really deploy it very easily. It works from scratch. I mean, you switch it on, and in 2 minutes you have the readings, which is not the case for both Picaro and LICOR instruments, so it's very convenient. However, it's not as precise as the other one. So, okay, we don't have time. So, going to the final part, we use then the screening method. This is our last method which we applied, and we just drive single passes around each of the facility. We apply very simple Gaussian equation, and we end up with the rough estimated. I mean, rough is plus minus 50% of the emission strength, and we know the distribution of the sources around the area of the single source. I mean, it can be single valve, or it can be single flange, or whatever else. And when knowing this distribution, we can correct this quantification of the in release rate by the other methods, and we end up with the estimation of the emission factors of the release rate. And usually the release rates follow this log normal distribution. So if you see this normal distribution here on the horizontal scale, this is logarithm of the methane emission rate, not emission rate. So if you see it in real life, it means that if you could repair, let's say, the 10% of the higher emission, higher released point sources, then you can reduce your overall emission by the, let's say, from 40 to even 90%. So this is really only with very simple and not very detailed trained people, you really can approach your infrastructure without touching it, and just propose which parts and where exactly are the leaks which can be repaired and help you to improve the emission overall. So finally, I thank you very much for attending this lecture, and also I would take advantage and invite you to Krakow. You can visit our city and take a run on the balloon which is installed, and recently we managed to make it also glowing, and now the color of the glow is related to the air quality index. So usually we hope it will glow in green, but sometimes of course it's still glowing in red, as Krakow was until recently one of the most polluted cities in Europe. Thank you very much again.
Thank you, Dr. Gausso. We move to our next speaker, Dr. Sebastian, and this time we'll be talking probably about climate change, performance index. So, yours.
Thank you very much. Hello, everyone. Thank you very much for inviting me to present at this conference. I'm very honored to be here to telling you about my work at the Environmental Performance Index. My name is Sebastian Bloch Munguia, and I am the new project director of the Environmental Performance Index. And I will talk today in particular about the indicators that we have related to air quality and climate change. Let me see. Aha. So the Environmental Performance Index is a collaborative effort of Yale University and Columbia University in the US that attempts to measure the state of the environment and sustainability in countries around the world. We just moved from presentations that covered different scales from like regional levels to like the vault level, and now I will tell you about this approach to measure sustainability in the whole world. So the scale and the detail of the analysis is quite different. But the EPI is driven by these three main principles. First, it is a data-driven analysis that tries to find the latest global data sets measuring different environmental issues and analyze them rather than relying on anecdotes to assess performance. Then we focus on environmental outcomes rather than on policy inputs. That is that we try to not reward countries simply by having certain policies codified into law, but rather we try to measure the actual effects of those policies and to see if they are being effective at their goals. And finally, we are committed to transparency, so we always aim to publish all our methodology and underlying data sets, and we use data that is publicly available for anyone interested to be able to replicate all of our results. And we are always happy to engage with the people that use the EPI, and we are very happy to receive your suggestions to keep improving our work. And this improvement is important to highlight because, let me see, where should I point this? I'm sorry. I don't know where to, there you go, sorry. Yes, I was saying that we're constantly trying to improve the EPI, which actually has a very long history. There are like, the EPI in some way or another has been present for over 20 years. And it is a report, an analysis that is published every 2 years. So the last one was published last year in 2022. And now, as the new project director, I am in charge of producing the next reports that will be published in 2024. So one of the main strengths of the EPI is that it condenses terabytes of data from different sources into a synthetic and simple to understand set of indicators that measure different aspects of sustainability. We calculate a score for each country in each indicator, and then we combine them into an overall score. So that makes the EPI a composite indicator. We can then analyze trends at the global or national level, and the range of topics that the EPI covers makes it one of the most comprehensive environmental indicators, both in terms of issues measured and countries covered. And that is why several countries have used it to track their environmental performance. And I'm very happy and proud that Oman is using the EPI as one of the key performance indicators to track progress in their Vision 2040 initiative to track progress in the environmental sustainability area. So, as I said, the EPI tries to measure environmental performance in all countries around the world. Currently, we were able to score 180 countries, showed here in blue. And for the remaining countries, we hope to one day be able to calculate scores as well, but currently we don't have enough data to calculate a reliable score. And even though the scope is global, it is very difficult and even unfair to compare all countries with each other because they have so different environmental contexts. So one thing that the EPI does to address this is to divide the world into 8 different regions, showed here in different colors, based on the geography, socioeconomic factors, historical factors, etc., so that countries can compare their performance with other countries in their peer groups. Although this is definitely not like written in stone, and we encourage countries to decide with which peers they want to compare themselves. So, for example, Oman, in the EPI framework, would fall into the Greater Middle East peer group, which is also called the Middle East and Northern Africa, the MENA region. And the results that I will present will be breaking down by these different peer groups. So, what issues does the EPI consider? In its latest form, the EPI includes 40 different environmental performance indicators, which are grouped into 11 different issue categories, themselves grouped into 3 main policy objectives, which are climate change, environmental health, with focuses on how healthy the environment is for people, and finally, ecosystem vitality, which focuses on the integrity of natural ecosystems and their biodiversity. Today, given the focus of this conference, I will talk mainly about 2 sets of indicators: the climate change, with measured trends in the emission of greenhouse gases, and air quality, which measures the effect of air pollutants on human health. So let's start with climate change indicators. Currently, the EPI has 9 different indicators of climate change. First, we have 5 indicators that measure the growth rates in the emissions of 5 of the main greenhouse gases: CO2, methane, nitrous oxide, fluorinated gases, and black carbon. All of this data comes from a data set called PrimeApp-HEAth, published by the Potsdam Institute of Climate Impact Research, that combines a variety of sources to calculate the historical emissions of different gases in different sectors and countries. So, given that it's difficult, again, to compare all countries with each other, they have different sizes, populations, etc., we focus on the growth rates. That is, are the emissions increasing or decreasing or stable? Because then it doesn't matter what country you are considering, the goal, the global goal, is to decrease emissions and eventually reach 0. So that is why we focus on the growth rates. And it says adjusted because we adjust for changes in GDP, because a country might have lower emissions simply because its economy is suffering some hardships, but that's not the way in which we want to reduce our emissions. The goal is to be able to maintain healthy economic growth while decreasing emissions, what we call decoupling, right? So that is the adjusted part. Finally, we have other indicators that use the same underlying data, but focus on different aspects. An important one is the projected emissions to 2050. This combines all the different gases, looks at the trend over the last 10 years, and then projects to see what the emissions would be in 2050. I will talk a little bit more in a moment. Then we also have the trend in greenhouse gas intensity, which considers the amount of emissions divided by the GDP of countries. Also, greenhouse gases per capita. Both of these indicators use population and GDP data from the World Bank. And finally, we also have an indicator of CO2 emissions from land cover that uses modeling outputs from the Million Group in Australia. Let me talk a little bit more about the projected emissions indicator, given that, as you can see, it receives a very large weight. Actually, I didn't mention, but this diagram, the size of the different slices, represent the weight of these different indicators in the overall score, how much they contribute, how important we consider them. So, given that the world has committed to reach 0, or at least net 0 emissions by 2050, the EPI team developed this indicator in the last iteration. And it works more or less like this. We have these different lines represent the total emissions of different countries as an example. And then we have a simple or even simplistic approach of fitting a linear trend to the last 10 years of data and then extrapolating it to 2050 to see what the emissions would be if countries continued with the trend in which they have been over the last 10 years. And the goal, as I said, is to reach 0 by 2050. Okay, so let's look at the results. What did we find? Here you can see the distribution of climate change scores, like the whole category of climate change indicators for the different regions and that I described. And as you can see, for the whole world, the overall score that ranges from 0 to 100, 100 being the best performance, it's 40. That is, the world is definitely not on track to meet its climate goals. Performance varies by region, but it's actually quite bad across the whole world. So the lines show the median value for each region, and then I also added with the dotted line the score of Oman in the last report, which for climate change was 23.2. This is not very good, but I mean, it's not surprising given that emissions have been increasing in Oman over the last 10 years. That's probably not going to continue, hopefully, but that explains the relatively low performance. But the encouraging part is that over the 10 years, Oman increased, almost doubled its score in climate change, because even though emissions continue to increase, they are doing so at a slower rate, which is very important. Okay, sorry, I need to accelerate. So let me move to air quality indicators, which focus on the effects on health. So there are two types. We have three indicators that actually measure how much different pollutants affect health, measured by DALI rates, the disability-adjusted life years lost per 100,000 people, which come from the Global Burden of Disease Initiative. Basically, how much people are dying early due to different pollutants. And for the ones in which this more advanced modeling of health effects is not available, we just consider the exposure that people get to different pollutants. Basically, we look at where the pollutants are being emitted based on satellite observations, shown here, for example, for nitrogen oxides. And then we look at where people live to see like how much people are being exposed to those pollutants. And then we calculate, the average exposure by country. And again, here are the same graph, but for air quality. Again, the world is not doing very well overall, although there is a lot of variation by different regions. Oman is also increasing in this category, which is encouraging. I need to highlight an important limitation, which is that currently we cannot distinguish between natural and anthropogenic sources of these pollutants, and especially for particulate matter. That's a great limitation for countries in arid regions like Oman, because we know that here, wind-blown dust, it's an important contributor to particulate matter, and the EPI should not be measuring that because it's not something that countries can really affect through their policies. So my take-home messages are that climate change and air pollution are clearly interrelated. They are two different consequences of the gases and aerosols that we are releasing into the atmosphere. The world is not on track to meet its climate goals or air pollution goals. But Oman is making progress, and this progress is very likely to accelerate with rapid expansion of renewable energy sources that are part of the energy transition plan of the country. Thank you very much for your attention, and I'm happy to take any questions if there is time later.
Thank you, Dr. Sebastian. Our last but not least, we have our speaker, Dr. Abdelmonem from UNEP. And Dr. Abdelmonem will give us some highlights from UNEP emission gap report. So.
السلام عليكم جميعا. Since the majority are Arabic speaker, I decided today to speak in Arabic. So I'm sorry for the non-Arabic speakers, so they have to look at the presentation. I have it in English, so you can follow, and I'm happy to share the presentation also in English and Arabic. السلام عليكم جميعا. عرض اليوم عن تقرير أو أحد تقارير اللي يقدمها برنامج الأمم المتحدة للبيئة، التقارير السنوية الخاص بتقرير فجوة الانبعاثات لعام 2022، نافذة الفرص على وشك الإغلاق، The Closing Window. هذا التقرير، الرسالة الرئيسية من هذا التقرير يقول أن التقدم المحرز الغير كافي في الواقع بشأن العمل المناخي يجعل التحول السريع للمجتمعات هو الخيار الوحيد المتاح. طبعا التقرير اللي أمامنا هو التقرير 13 لبرنامج الأمم المتحدة للبيئة. سبقتها العديد من التقارير بشكل سنوي. عادة تعرض أو تطلق هذه التقارير قبيل انعقاد مؤتمر الأطراف، الكوب المختلفة. فالتقرير 13 تم إطلاقه في شهر أكتوبر الماضي قبل انعقاد الكوب 27، ويعرض لمحة عامة عن الاختلاف بين النسبة المتوقعة لانبعاثات غازات الدفيئة في عام 2030 حسب الكوميتمنت اللي قامت بها الدول، والنسبة التي يمكن أن نصل إليها لتجنب أخطار أو آثار التغير المناخي. هذا التقرير تم إعداده في الحقيقة من حوالي 77 مؤلف expert, international expert coming from 21 countries، يعني من 21 دولة، وكان فيه لجنة دولية أو steering committee هي اللي تقوم بمراجعة ومتابعة تنفيذ هذا التقرير، بالإضافة إلى عملية ريفيو طويلة تمت عن طريق ما لا يقل عن 100 external reviewers قاموا بمراجعة هذا التقرير. وكذلك الدول التي ذكرت في التقرير أعطيت الفرصة للنظر إلى البيانات الخاصة بدولها اللي تم عرضها في التقرير to validate الداتا وتعطي أي ملاحظات قبل إطلاق التقرير. طبعا العرض اليوم قسمته إلى جزئين. الجزء الأول حنتطرق للتقرير الأخير اللي هو 13، حنشوفوا بعض الريزلتس وبعض النتائج المعروضة فيه، والجزء الثاني حيكون ملخص للنتائج الرئيسية اللي يقدمها التقرير. طبعا التقرير يطرح سؤالين مهمين، two questions يعني addressed in this report. السؤال الأول إنه هو ما مدى التقدم المحرز الخاص بالإجراءات والأكشن من الفترة ما بين الكوب 26 والكوب 27. السؤال الثاني how can we initiate ولا accelerate، يعني كيف نقدر نقوم بعملية تسريع والقيام بمبادرات أكثر لعمليات التحول اللي هي transformation. للإجابة على هذه الأسئلة قام الباحثون بالنظر إلى الترندز في الجلوبال جرين هاوس جاس إميشنز والأبديت الخاص بالمساهمات المحددة وطنياً. كذلك ما يميز هذا التقرير أن فيه فصل أو تركيز خاص بمجموعة 20 اللي ما يسمى بالجي 20 countries. وزي ما تعرفوا حضراتكم أن الجي 20 countries مسؤولة عن أكثر من 80% من الانبعاثات العالمية. التقرير أيضا نظر إلى أو الباحثين نظروا أيضا لما قدمه الساينس من حيث البروجكتد تمبريتشر انكريز والسيناريوز وكل ما يخبرنا به العلم فيما يتعلق بالإميشن جابس ل 2030. كذلك التقرير قدم أو ركز على 4 قطاعات رئيسية فور سيكتورز يعني اللي هن مسؤولين بشكل كبير على مسألة الانبعاثات. هذه القطاعات اللي هي امدادات الطاقة، الصناعة، البنايات والمواصلات. بالإضافة إلى ذلك ركز التقرير على أنظمة مهمة جدا لها علاقة أيضا بالانبعاثات، وهو النظام الغذائي اللي هي الفود سيستم، وكذلك الفاينانشال سيستم أو النظام المالي. طبعا مش هنغوص في البيانات لأن فيها كثير من الديتيلز، بس بشكل عام يعني التقرير يعرض نتائج عديدة خاصة بالانبعاثات. على سبيل المثال هذا الفيجر يبين لنا أن فيه يعني انخفاض في معدل الانبعاثات، خاصة لو تلاحظوا في عام 2021 أثناء فترة الكوفيد كان في انخفاض للانبعاثات بسبب الكوفيد ريستريكشنز والأمور اللي نعرفها كلها، ولكن هذا الانخفاض كان مؤقت، وبعد ذلك شهدنا في زيادة في الانبعاثات بعد الانفراج. بالنظر إلى خريطة العالم، هذه الخريطة تبين الابديتد انديسيز او يعني ما قدمتها الدول، التقارير اللي قدمتها الدول او الالتزامات اللي قدمتها الدول منذ الكوب 26. ونلاحظ ان حوالي 90 اكثر من 90% في الواقع من الدول قدمت ابديتد انديسي، وهذا يدل على اهتمام الدول بهذه المسألة. طبعا زي ما ذكرت أن التقرير يركز على مجموعة ال20 G20، ونلاحظ أن للأسف أن مجموعة ال20 يعني they are not on track زي ما نقولوا، يعني المطلوب منهم الكثير من التعديل وتسريع السياسات الخاصة بالانبعاثات. طبعا هذا التقرير هذا الفيجر أيضا يبين السياسات المختلفة وتأثيرها على فجوة الانبعاثات. هذا الفيجر يبين التباين الواضح بين دول ال20. طبعا دول ال20 هي الدول الصناعية الكبرى، فزي ما تلاحظوا أن فيه اختلاف في ما بين الالتزامات اللي تقوم بها هذه الدول وبين الانبعاثات على الواقع. وهذا التباين طبعا يعطي انديكيشن أن فيه الفيزيبيليتي غير موجودة لحد الآن من هذه الدول الكبرى. هذين القطاعات المختلفة السيكتورز الفور سيكتورز، وفي تحليل لكل سيكتور زي ما تلاحظوا حضراتكم. الالكتريسيتي سبلاي اللي هو امدادات الطاقة هو الأكثر قطاع متقدم في مجال خفض الانبعاثات. القطاعات الأخرى طبعا عليهم الكثير من القيام، خاصة بموضوع التكنولوجي وتسريع عملية تخفيض الانبعاثات. الفود سيستم طبعا زي ما ذكرنا ان هذا احد النظامين المهمين في مسألة الانبعاثات. زي ما تلاحظوا حضراتكم ان الفود سيستم مسؤول عن ثلث الانبعاثات العالمية اللي تأثر على طبعا الكلايمت تشينج، هي تأتي من الفود سيستم، وبالتالي في تركيز كبير على هاو تو ادرس مشاكل الخاصة بالفود سيستم. الفاينانشال سيستم طبعا أجين نفس الفكرة، حتى هو يحتاج إلى كثير من الريفورم، والتقرير يعرض مجموعة من الأوبشنز أو الخيارات لعملية إصلاح النظام المالي. يعني بشكل عام التقرير يرسل رسالة قوية جدا للدول أن الكثير من التحول مطلوب للإيفاء بالتزامات اتفاق باريس. الآن ننتقل إلى الجزء الثاني اللي هو ملخص لبعض النتائج الرئيسية أو الرسائل الرئيسية في التقرير. نعم دقيقة. حناخذ منها 3 رسائل رئيسية عشان الوقت. الرسالة الأولى أن أزمة المناخ تستدعي تحولا سريعا للمجتمعات. زي ما نلاحظوا أيضا على الرغم من الدعوة إلى تعزيز المساهمات المحددة وطنية للNDC ل 2030 كان التقدم المحرز منذ الدورة 26 لمؤتمر الأطراف في غلاسكو غير كافي على الإطلاق. طبعا هذا التقرير قدم السنة الماضية وحيقدم تقرير آخر اللي هو السنة هذه بإذن الله قبل انعقاد مؤتمر الأطراف ليعكس فترة الفجوة بين الكوب 26 وال 27 و 28. الرسالة الأخيرة اللي حنختم بها: يحتاج العالم من أجل المضي قدما في المسار الصحيح إلى تقليل غازات الاحتباس الحراري بمستويات غير مسبوقة عن السنوات ال8 المقبلة أو ال7 سنوات القادمة إن شاء الله. وشكرا على الاهتمام والانتباه، والسلام عليكم ورحمة الله.
طيب إن شاء الله. Can we get the microphone? Okay. Thank you, Dr. Abdelmonem. جزاكم الله خير. I'm sorry I was rushing the speakers because of the limited time, and we'll open the floor now for the audience to ask questions. We have Dr. Abdelmonem who is going to leave soon, so maybe we can start with question to Dr. Abdelmonem if you have any question for him. So please, we can start with the last speaker. So the floor is open for the questions from the audience. We have almost like 5-10 minutes. Well, in that case, then we'll open the floor for any kind of questions. Dr. Ali, okay. If you can introduce yourself shortly and then the question directly.
السلام عليكم. My name is Ali Alawi from video. سؤالي للدكتور عبد المنعم: لما تكلم عن السلسلة الغذائية، هل تقصد من بداية الإنتاج الغذاء إلى نهايته مع المعالجة؟ تعرف طبعا نسبة كبيرة من الانبعاثات تكون في إدارة النفايات، هل تقصد يعني كامل السلسلة؟ شكرا دكتور.
شكرا دكتور علي، وسعيد بلقائك بعد 5 سنوات تقريبا. وفعلا يعني سؤال مهم جدا خاصة بالموضوع الفود سيستم. طبعا الفود سيستم ننظر له يعني الهول سايكل، ابتداء من البداية إلى النهاية، including الفود سبلاي تشين وكل هاي الأمور. هذه كلها كل خطوة من خطوات الفود سيستم تؤثر في عملية الانبعاثات. وزي ما ذكرنا أن يعني النظام الغذائي بالذات مهم جدا للتركيز عليه، لأنه هو مسؤول عن ثلث الانبعاثات، وبالتالي كل جزئية من جزئيات النظام الغذائي مهمة في تخفيض الانبعاثات العالمية. وشكرا على السؤال. شكرا دكتور.
شو اسمه؟
In the back there. Anybody moving the microphones? And please try to direct your questions to specifically which our speakers.
شكرا سيد منعم. عندي سؤال بالنسبة للتغيرات المناخية. هل تعتقدون أن مع أن تكاثر السكان في العالم لن يكون له تأثير خصوصا على هذا التغير المناخي، بحيث أن تكاثر السكان يعني بطريقة أو بأخرى يعني تكاثر موارد الأكل إلى ما ذلك، وما شاهدناه من انبعاثات من الميثان، وتعرفون أن هناك علاقة بين الميثان والغذاء. هل تعتقدون أن اليوم الكوكب يسير على الطريق الصحيح؟ وشكرا.
So, Dr. Sebastian, I thought he directed to Sebastian. Dr. Sebastian? Okay, Dr. Abdelmonem, تفضل.
You can answer if you want.
Almost to translate that.
شكرا على السؤال. طبعا احنا في يعني خلال عمليه التقييم البيئي اللي نقوم بها في عندنا ميثودولوجي نتبعها في العاده، اللي هي اللي يسموا فيها DBSIR framework، يعني قياس اطار لقياس او تقييم البيئي المتكامل. أول شيء نبدأ بالنظر إليه هو موضوع البوبوليشن جروث. فموضوع النمو السكاني هو ننظر له نحن المين درايفر لعملية التغيير البيئي. فمسألة النمو السكاني مهمة جدا في عملية التقييم، وطبعا لها تأثير مباشر غير مباشر على الوضع البيئي. غير مباشر نقصد به أن كل ما زاد عدد السكان كل ما يزيد الاستهلاك، كل ما يزيد من استنزاف الموارد الطبيعية وغيرها من المؤثرات الأخرى. وبالتالي موضوع النمو السكاني هو يعتبر نحن نعتبروه درايفر أو من القوى المحركة لعملية التغيير البيئي. طبعا بالنسبة للشق الثاني من السؤال، يعني كل البرزنتيشن أكدوا أن العالم يعني ليس على المسار الصحيح في مواجهة التغير المناخي، وخاصة الاتفاق اللي صار في باريس أو اتفاق باريس أن تخفيض درجات الحرارة إلى 2 درجة مئوية أو تحت 2 درجة مئوية 1.5. هذا يتطلب الكثير من الجهد، لحد الآن كل التقارير العلمية تبين أن العالم يعني لا زال يحتاج الكثير من التسريع والتحفيز للوصول إلى الهدف المنشود اللي هو اتفاق باريس. وشكرا على السؤال مرة ثانية.
شكرا دكتور منعم. I have seen a hand raised before there. I'll come back to you. So over there, the mics.
Assalamu alaikum. My name is Abdurrahman Al-Shahi. I'm Director of Performance in Saudi Arabia. First of all, I'd like to thank the Sultanate of Oman for a wonderful organization and a very hospitable reception. We really enjoyed the content and the organization of the event. So thank you very much. I also want to thank the panelists. All the presentations were very insightful and helpful. I learned about new kinds of economies, so I need to refresh my knowledge of that space. Also, we did see some excellent research work in terms of measurements for emissions, and I definitely want to visit Caraco now, see what's there. My question will be directed to Dr. Sebastian. I'm very interested, as we discussed yesterday, about the EPI report. When it comes to the air quality parameters, we noticed that the weight distribution for some KPIs can be unfavorable to countries or depending on the nature of the country. For example, the solid fuel component covers almost 4% of the whole score, while in our region we don't really use that much coal or wood to cook food anymore. You know, we rely on gas, we are a petrochemical region, and we spend a lot of effort to reduce our emissions from that area. So if we do that effort, it will not reflect much on the score overall. So how can you alleviate this issue and make sure that it's balanced and fair to all countries? Thank you.
Thank you very much for the question. You bring up a critical issue and challenge of doing this global scale analysis, and that is how to develop indicators that are relevant for all countries. That is very difficult because, as I mentioned, the conditions vary a lot. So the way the EPI team assigns weight to the different indicators is based on 3 main principles. First of all, we gather input from a variety of sustainability experts to try to assess what is the perceived importance of different environmental issues at the global scale. And of course, some issues will be more important for some countries than others. Then we also consider the quality and reliability of the data, including for how long do we have it, how frequently is updated, etc. And there's a final, more complicated aspect, which is related to the statistical correlations between different indicators, which means that sometimes we cannot assign too much weight to certain indicators because they are already correlated with others that have a high weight, and therefore we try to take that into account when assigning weight. So addressing now your question more directly, if in your country, like household fossil fuels are not very common way of cooking food anymore, then you should be scoring well in that indicator because there is not much pollution in that aspect. And by just focusing in general on increasing your environmental performance, that ideally should be reflected in the scores. I think one of the, as I mentioned, one of the most important limitations at the moment of these air quality indicators, which is very relevant for the countries in this region, is that we are not distinguishing between the natural and anthropogenic sources of pollutants. I'm excited to say that there is new research being published recently that will probably allow us to disentangle these two components in the next report, and that should, simply by that changing the methodology, the air quality performance of countries in arid regions is very likely to improve. Well, at least in the EPI scores. I hope that answered your question.
Thank you. The mic in this. Okay. خلاص. Go ahead, Prof. Yasin.
Yeah, thank you. I have a question for Sebastian regarding the calculation of greenhouse gas emission.
Okay.
Calculation. Okay. You got.
تفضل بروف ياسين تفضل.
Okay, I have a question for Sebastian regarding the calculation of greenhouse gas emission. For Oman, 20% of the emission is coming from HFCs. And HFCs, because we are head country, and now we use about 2 million tons per year, so we're going to increase of the coming years. My question, why should we integrate it and the greenhouse gas emission HFCs? Because Oman is a hot country. If you compare Oman to another country, which is not situated in hot region, we're not going to use HFCs. For this reason, HFCs should be kept out from calculation of greenhouse gas emission to get a clear idea, more accurate idea about the real emission coming from other industry or other parts of the economy. You got my point?
So, you mentioned HFCs? So
because HFC is hydrofluorocarbon, which is used in refrigeration and air conditioning. We are a hot country. We don't have other alternatives. Only to use this gas. And you know this gas, they have global warming potential from 2,000 up to 12,000.
Yes.
And they create big jump in the greenhouse gas emission in Oman. Why? Because we don't have any alternatives. If the government decided to phase out all these gases, will take most likely 40 to 50 years. And we don't have alternatives up to date if you take safety and moving to other natural refrigerant. You got my point?
Yes, I definitely got the point. I'm not sure I see that perhaps you don't have so many alternatives. That's a very good point. Again, the EPI should be measuring things that countries can really affect through their policies, right? So you raise a valid point that is perhaps not so easy to address. At the same time, that indicator receives a relatively low weight in the overall structure of the EPI. So if you focus on decarbonizing the rest of your economy, reducing your CO2 emissions, methane, which was emphasized, then it should be entirely possible to reach your sustainability goals and increase your EPI score dramatically, even without considering the HFCs as a priority at the moment. Hopefully there's new technology that can offer new alternatives to have better cooling systems. But yes, I take your point, and I'm open to suggestions of which other ways we could
because now we are working maybe to develop some suggestion for UNFCCC to change these categories, because this category, they embedded HFCs under greenhouse gases. It should be kept out in order to reflect the effort of the country for dioxide, for methane, for oxide nitrides. But we don't have up to date any mature technology for refrigeration, because refrigeration, we cannot use propane for a safety reason, or using carbon dioxide for safety reason. We need to really think about this point for the calculation of your EPA.
Yeah, thank you very much for the suggestion.
Thank you.
We are running out of time. In fact, I know that there are lots of questions to ask our speakers here, but because of the next parallel session will start at 11, and we need a break in between. I would like to thank you all for your attention and joining us this session today. And I would like also to thank my speakers one by one. Thank you very much for your contribution today. And hopefully we'll see you in the next session as well. Thank you very much.
Thank you. Thank you, Dr. Am. I have a short statement for tomorrow morning. Tomorrow we will have the closing ceremony. After the closing ceremony, we have a social program, and we will have a desk for registration of names. Persons who are interested to join us for the social program, which will start, I think, by 11. We will have social program of 3 hours, followed by traditional lunch. Please, there is a desk here when you can register your name and to join us for the social program. Now we will have coffee break, very short coffee break, and we come back to this room for the 2 workshops. And also other participants interested for the scientific program of the conference, we will have 4 parallel sessions in the rooms beside this room. Thank you very much. Thank you.